Okay, so hello again and welcome to the second part of our webinar on scaling up linked data. So quick summary of what we discussed already during the first part of the webinar. We briefly introduced big data and how linked data actually can be beneficial for various big data scenarios for dealing with high volume, velocity and variety data. We also outlined various approaches of how big data can contribute, can improve managing large volumes of linked data. How these two technologies can actually contribute to each other. And in particular, we discussed several alternative approaches for utilizing NoSQL databases, column stores, or document stores for managing and querying RDF data. So, excuse me. Something very important that we haven't talked about so far is reasoning. How do we, this is a key feature of RDF, semantic technologies, linked data in some cases. So how do we perform efficient reasoning and inference of new information based on the standard inference rules predefined from the RDF or web ontology language standards. And all these systems that we discussed already, the NoSQL-based systems used for storing and querying RDF data, they were actually not suitable and for reasoning, for large-scale reasoning with this data. So we will outline some very promising approaches for utilizing Hadoop for distributed large-scale materialization inference of new triples based on existing triples. A very important problem when you work with semantic data, with RDF data. So yeah, just a few seconds of quick introduction. Basically, Hadoop is the implementation, the open source implementation of MapReduce. MapReduce is a framework for distributed batch processing, large volumes of data. Relatively easy, relatively simple design, map phase and reduce phase. The map phase provides some partitioning of the input data, so that so the input data is basically distributed on a cluster. And in order to efficiently process it, you need to aggregate and partition and aggregate it somehow. So the map phase is responsible for the partitioning of this distributed data. The reduce phase is responsible for performing the aggregated computations over the individual partitions. Basically, if you have big clusters with several nodes, each node will be in the end responsible for dealing with one specific partition. So relatively simple yet efficient way to process in parallel large amounts of distributed data. As we said already, MapReduce, the MapReduce paradigm and Hadoop is not really suitable for operations which require low latency, basically distributing tasks, scheduling tasks on the cluster. Some data copying may be required between the nodes. These are tasks that have negative impact on low latency job requirements. So MapReduce is really very well suited for offline batch processing of really large volumes of data, not so much for millisecond response times and really low latency response times. So yeah, basically, usually Hadoop is deployed on large clusters, tens, hundreds, thousands in some cases of nodes. The really core component is the distributed file system, HDFS. And yeah, basically each node in the cluster is responsible for processing its local data and contributing to part of the overall processing of the data. Scalable distributed reasoning with MapReduce, one of the, not the first, but one of the first very extensive evaluations of the suitability of Hadoop for reasoning of really large RDF data sets. What is the approach? We know that on the one hand, we know that Hadoop is suitable for distributed processing of data. On the other hand, the RDF materialization, the RDF reasoning and inference, inferring new data from existing triples, from existing RDF data, has its specifics. So it's not really trivial to just design the map phase and the reduce phase and to get really optimal performance. This is the actual contribution of this research, investigating investigating specific problems related to implementing RDFS reasoning on top of the MapReduce paradigm and proposing concrete optimizations and solutions. So, very brief overview of this excellent research. The idea is to implement the RDF rules. So, just a quick reminder: standard RDF rules that define how new data is basically inferred from existing data in the RDF database. So some of the rules are trivial, so to say. Basically, they have only one part on the left-hand side. So inferring the new information on the right-hand side is, so to say, trivial. But other rules actually are joins. They require joining two triples and inferring some new information based on these these two triples. An example, for example, is this is the transitivity rule for classes. So, for example, rule number 11. If we know that if we have a statement in the database, a triple in the database, stating that some X is a subclass of Y, some class is a subclass of some other class, and then another statement that Y is a subclass of Z, then the inference engine or the RDF database will infer the transitive closure based on these two facts, that actually X is also a subclass of Z. So these are the standard RDF rules that each RDF database or reasoner complies with when inferring new data. And so the idea of this, the idea of utilizing Hadoop and MapReduce for these reasoning rules is to implement each RDF rule as a map and reduce function. So why do we need this? As I said, the data is distributed on a potentially large cluster. So in order to efficiently perform these two joins, the two triples that are required for the join may actually reside on a completely different nodes in the cluster. So each node actually has only a partial view of the data available in the system, and it is not able to compute the complete closure of this RDF set of statements on its own. Basically, some data needs to be efficiently exchanged so that these joins can be performed, and this is why the map and reduce functions are used. As I said, the map function can provide some partitioning of the data space so that the proper data can be aggregated for the reduce function, and the reduce function can use all these data as input to provide some computation. In this case, the reduce function performs the actual join and the map function is responsible for efficiently properly partitioning the data space so that the triples which may be used on the left-hand side of some rules may be collocated together in the same partition, and they can be used for the inference process. A few more details. Basically, the mappers and the reducers, they work in the mappers. They work in terms of key value pairs. So they, when they process the input data, they basically output a key and a value. The value may, of course, be arbitrarily complex object. Basically, the key specifies which partition this piece of data should belong to, which reducer will, in the end, get access to this data. And excuse me. The reducer will receive all the full partition, all the data which is relevant to the task that he is supposed to perform. So basically, this means that the mapping phase, of course, mapping phase outputs as a value the original triple. It is required for the join. We need access to the original triple, so naturally, the original triple is the value of this key value triple. But the question is, what is the key? Well, the key is actually the term that we are joining on. And so, for example, rule 11 that we discussed already, the transitivity rule for classes. The joining term in this case is y. So for the first triple, the joining term is the object, but for the second triple, the joining term is the subject, which means that depending on what kind of triple the mapper is processing, the key will be either the subject or the object of the triple, basically this specific term which will be used for the join. And this ensures that the reducer receives all the required information to perform the join. And yeah, this is an example of how the mappers produce these key value pairs where the value is the original triple and the key is either the subject or the object, so that the reducer can get access to the constituents, the triples that will be used for the join and for inferring new information. Okay, so this is a very brief summary of the approach. How do we map the RDF reasoning rules into the map reduce paradigm? But of course, there are many challenges. This trivial implementation actually doesn't perform very well. And the reason for the suboptimal performance is that basically there are too many duplicates. So there are duplicated triples which are produced by alternative rules. And the evaluation that the authors performed in the test scenario, basically the duplicates outnumbered the unique triples almost 50 times. In some other approaches that we will briefly discuss later, this ratio is even worse, actually. So duplicate removal is definitely a challenge and not a trivial task to overcome. Concrete optimizations on top of this naive approach that we already described, concrete optimizations to speed up the processing. So replicate the schema triples on each processing node, keep them in memory so that they're easily accessible. So what is the rationale? The rationale is that schema triples are actually required for each join. Basically, each join, each rule that has two triples on the left-hand side, at least one of the triples is a schema triple, like a subproperty or subclass. Which means that for joins, these schema triples are always needed. And so this is the first requirement. And the second requirement is that usually the set of schema triples is relatively small as compared to the set of just instance assertion triples in the database. So it is actually feasible to replicate this relatively small set on each processing node and to keep it in memory. Another very important optimization, reordering of the rules. Basically, we mentioned that when these rules are basically applied when the reducers apply the joins and they produce new information, new triples, then these new triples may be used as input and they may activate new rules which may generate even new triples. Basically there is, it becomes complex there may be many iterations required until the system reaches the full closure and a fixed point. So the authors propose a specific reordering, rule reordering, so that they prevent the situation where one rule can fire another rule, can fire a rule which has already been executed. So in a way, they ensure that some sequential phases may be expected when applying these rules. Sorry. Yeah. So this is the concrete ordering that is proposed by the authors. This rule reordering is also used by other research prototypes later. And results, the interesting part, throughput of 4.5 million triples on a 16-node cluster. This is actually the evaluation that the authors performed with DBpedia on a distributed Hadoop cluster from up to 64 nodes. And we can see that around 16 nodes, basically the performance doesn't really improve. Basically, new nodes, this is the point of diminishing returns, where adding new computational power does not really significantly speed up the results, the final computation. Of course, this is not something specific to RDF reasoning or to these 15 RDF rules or to the specific approach that the authors recommended for mapping RDF reasoning rules onto the MapReduce paradigm. This is more or less a limitation of Hadoop. Basically, the challenge with Hadoop and with such distributed systems in general is that it's very difficult to ensure that all the nodes in the cluster are equally loaded with tasks, with data. And usually the case is that some nodes may be overloaded because, for example, the rules that they're responsible for are activated a lot by the current data distribution, and while some other nodes are not performing, not busy. The larger the cluster, the more difficult it becomes to ensure this optimal loading of nodes. It may be the case that some nodes are overloaded, some nodes are underloaded. Plus, there is, of course, the overhead of scheduling, starting, restarting, of course, in the case of failures of Hadoop tasks. So eventually, these joins that each reducer performs are usually not so complex, so that a lot of tasks need to be scheduled and started on the cluster, which means its efficiency will be reduced. Something related from one of the lead authors from the Free University of Amsterdam, Jacopo Urbani. Lessons learned from large-scale reasoning. Basically, we outlined some of these conclusions and these lessons while discussing the RDFS reasoning on top of Hadoop. Excuse me. So, the three so-called laws of large-scale RDF reasoning. The first law is treat schema triples differently. We outlined already the rationale behind this decision, behind this law. And the solution is replicate, if possible, replicate the schema triples to all nodes to minimize subsequent data transfer between nodes. These triples will be required for every join. And this set is relatively small. It's usually a very small fraction of the full RDF data set. So it is feasible to distribute it and keep it in memory. Second law, the data skew dominates data distribution. Basically, we're talking about distributed data cluster, so tasks are moved to nodes where some particular piece of data resides, which means that we come again to the problem that we discussed, that depending on how the data is distributed, partitioned across the cluster, there may be very different performance results for some specific computational tasks. Basically, how much some nodes will be loaded, will they be overloaded, some nodes may be underloaded, and there may be some extensive data exchange required between different nodes. Basically, this depends a lot on what kind of data you have, what is the skew in the data you're working with, and some smart strategy for providing an optimal data distribution may be required, and it will be specific to the particular use case you're solving and to the particular data you're working with. And the third important lesson, the third important law, certain problems only appear at a very large scale. And this is, again, not really specific to like RDF reasoning. This is true for every big system, complex systems processing lots of data. And the point of the author is that a lot of these prototypes that we see for efficient reasoning, efficient query, distributed query, they work well, but only on limited proof of concept prototypes. But if you really want to apply it on a web scale, on a really large scale, and really process realistic volumes of data and realistic query workloads, then specific problems will occur, which will not occur at a smaller level, at a smaller complexity level. So memory management problems, optimization of various parts of the system, proper configuration of the various components which are involved in your system, which comprise your system, efficient communication between modules. Basically, all these tasks which in a small test scenario and a proof of concept scenario are not really important. Basically, squeezing a few milliseconds here and here is not really important, but it becomes important when you're actually working with really huge real-world data volumes and query volumes. So this is also something important to keep in mind when designing systems that are supposed to really handle real-world large volumes of data, web-scale data for RDFS reasoning. And yeah, moving on to the next section of the webinar, stream processing for linked data. So far, basically, we outlined NoSQL databases for data storing and data querying, MapReduce, Hadoop for data reasoning. So these are all aspects related mostly to the volume, handling bigger volumes of data. We didn't really talk so much about the velocity aspect of big data, basically working with real-time or near real-time data streams, Internet of Things scenarios. And this is what the focus of this section. So streaming data, what is streaming data? Basically, large amounts of new data which are continuously being generated, or maybe existing data continuously being updated and changing at a rapid rate. Examples, real-world examples are traffic data in a big city, sensor networks that generate lots of measurements, really simple measurements, but at a really huge, rapid rate. Social networks, the amounts of data generated per second on Facebook or on another big social network is really huge. Financial markets. So the challenge is that basically we're dealing with a lot of data sources which constantly provide lots of updates, and there is a stream of information which is not very trivial to process. And so it's not really practical to apply traditional data management approaches, data warehousing, for example, where we just gather and store all the data in a centralized or maybe distributed repository, and then we query it. This is not practical for two reasons. First, the data volume, because of this high velocity, it means that the data volume will actually be really huge, enormous after some period of time. And the second reason why such gathering and querying approach, traditional approach, is not really feasible is because of the recency aspect. Basically, most recent data is usually in such streaming scenarios. More recent data is more valuable. So, for example, you're usually interested in the traffic information as of this moment because you are participating in the traffic or you are planning something in the traffic. You're not really interested in the traffic information from 1 year ago unless you are doing some complex modeling or, I don't know, some prediction analysis, something like this. But usually the recent data is the most important. Gathering and storing all these data will have, again, will reach the point of diminishing returns pretty soon. And, excuse me, another challenge is that unlike traditional data management approaches where we query some static data and we get a response, the focus here is more on continuous queries, which basically provide results as new data enters the systems, new data satisfying the query restrictions entering the system. The query will provide a non-stop feed, non-stop stream of results. So this is quite different from the traditional data management and querying approaches. Stream processing. An important notion is the notion of a window, usually some sliding window, basically the active subset of the stream that we are processing, that the queries are analyzing and processing. So the other notion is the continuous query. It's registered basically on some stream, and with some sliding window, it processes part subsets of this stream, and it produces maybe a new stream of results or answers on its own. Of course, the continuous query is not limited to only working with the streaming data. It can also utilize some static data, some background knowledge for the query evaluation process. Since we're talking about linked data and applying scaling linked data for big data scenarios, and in this particular case for the velocity aspect of big data, what are the challenges, benefits and challenges of applying linked data in such scenarios? So, of course, the challenge is the different data sources, the data generated by these different data sources, maybe sensor networks, maybe some other data sources. Linked data principles allow us to enrich it with some metadata, and this metadata basically can be utilized for better data integration, data discovery over these heterogeneous data sources. But apart from these advantages, of course, there are specific challenges. So, for example, RDF triples, they must be annotated with a timestamp in order to keep the time-related aspect, the temporal aspect of these streams, that some events happen at some specific time point. Extensions to the SPARQL language are required. We already introduced continuous queries, so windows, various streaming operators which define the behavior of the streaming of the continuous query. The standard SPARQL 1.1 language does not target this kind of data, this kind of query scenarios, which means custom extensions are needed to the SPARQL language in order to utilize streaming data in a semantic RDF linked data context. Continuous semantics, again, different semantics for a static query versus a continuous query. Scalability is very important. The point of using such streaming technologies is that you usually want to process really large volumes of data. So performance is, again, very important. This is the whole focus of this webinar, how we can improve the performance of linked data storage management and querying using a variety of approaches. And in particular, related to the velocity aspect of big data, low latency and high throughput is really desirable for this kind of systems. We already mentioned that some of the systems like Hadoop, MapReduce, they are not usually applicable for such low latency, high throughput scenarios. They're more optimized for batch or offline jobs handling really huge volumes of data. Approximate reasoning may also be a viable alternative if exact reasoning is too expensive or too slow, basically violates one of these requirements for scalability or velocity. As you can see, lots of challenges related to applying semantic technologies to this streaming scenario. It's not really the case of taking these technologies out of the box and successfully adapting them for such scenarios. Excuse me. So, querying streams with SPARQL, as I said, specific extensions are required in order for this to happen. So we will outline two specific approaches, SPARQL and SPARQL streams for continuous queries. As I said, basically, continuous queries are different from static queries. Basically, they provide new results as new data is entering the stream or the window that they operate on. Yeah, SPARQL and SPARQL stream are based on their extensions of the SPARQL standard, and also they provide operators from the continuous query language CQL. SPARQL, so yeah, the input model of the data is RDF streams, as I said already. A standard RDF triple annotated with a specific timestamp, so that we know at which specific time point this event happened. This triple was true. And the specific extensions to the SPARQL queries. So, as you remember from the previous webinars on consuming linked data with SPARQL, basically you can specify how you get, for the specific query, you can specify where you get the data from, which named graphs maybe you want to combine. And in a similar way, SPARQL provides an extension for specifying which stream you want to consume data from. An extension about defining the window over this stream. So as we said, the continuous query does not process the full stream. It processes slices of this stream, windows of these streams which are sliding in time. And basically various options for configuring the behavior of how the window is specified. It could be limited to a specific number of triples and provide the first n triples of some stream. It could be time-based, it could be sliding. So basically various options to define how windows are defined over the stream so that continuous query can efficiently consume information. And another extension is the registration of the continuous query so that the execution engine can start executing the continuous query over the sliding windows of the stream. And this is a concrete example in C Sparkle. So as you can see, basically it looks very much like a standard Sparkle query, except for two things: how we register the query. Basically, this way we register a specific query over the stream. We register our query, we specify the stream that the query should consume. And we also specify the window that the query will consume data from. So in this particular case, the window is restricted to 40 seconds of data, and it slides, it's refreshed every 10 seconds. So a more graphical representation of what happens is basically this is how when some data enters the system, this is basically how it first enters one of the sliding windows, then the next one, and eventually this data will, the time point where this data was active will fall outside of the sliding window. So the continuous query will actually stop processing or analyzing this data. Excuse me. Sparkle stream, very similar approach to C Sparkle. Again, an extension of the Sparkle query language. Again, the input is an RDF stream, an RDF triple annotated with a timestamp, and again we have extensions for specifying the stream and the window, various options for configuring the window. And this is again example in Sparkle stream, more or less a standard Sparkle query, except for the definitions of the streams and the definition of the window, the sliding window specification. But apart from that, basically you still see the standard triple patterns that can be used with Sparkle. And so yeah, we briefly introduced two approaches for RDF stream processing. There are a few more, and this is a comparison, again, presented at the recent conference. All the alternatives basically have specific advantages and disadvantages depending on what kind of data, what kind of usage scenario you deal with. There may be different most optimal solutions. And something else related to working with streams, and RDF streams in particular. The semantic sensor networks activity at the W3C. So basically the result of this activity was an ontology used to describe sensor information, data, sensor networks. And also this semantic sensor networks working group, it provided recommendations and best practices for applying the semantic sensor network ontology to various scenarios dealing with real-time streams or large sensor networks. And yeah, basically without getting into too many details, the ontology provides different perspectives on how data is processed in such a sensor network. We have the sensor perspective, the data perspective, system perspective, various aspects related to the deployment of the sensors and the system. Yeah, moving on to the final section of the webinar. Basically, we'll briefly outline very quickly a few additional examples for successfully applying linked data in big data scenarios where volume, velocity, and variety are challenging. I mentioned already the trillion RDF triple use case by France in the United States. Basically, without getting into details, the use case was for applying linked data in RDF for the customer management database of a big telecom. So the resulting the data that the RDF database had to store on a really big machine was up to 1 trillion RDF triples. Basically, this goes to the point that when people think about linked data, they should not really limit themselves to the current volumes of the linked open data cloud, because this is really only a very small subset of a typical enterprise data being processed. And enterprise linked data scenarios usually have much bigger requirements in terms of volume, velocity, and variety than we can expect just by processing the linked open data cloud. Another interesting development, the Eureka Appliance by Yark Data, a subsidiary of Cray, the supercomputing company. So Eureka is basically a big data appliance for graph analytics and RDF analytics. It is basically a supercomputer, 1 terabyte of RAM, 8,000 processors. It provides an in-memory RDF database with SPARQL 1.1 support. So again, a high-end appliance which is available for processing really huge volumes of RDF data or linked data. One more very interesting research from Norman Heino and Jeff Pan. So we briefly presented the Hadoop, the MapReduced based approach for scaling RDF reasoning. So this is basically a shared noting scale out approach. Shared noting because the nodes in the Hadoop cluster, they're independent from each other basically. Each node stores a small subset of the data set and is responsible for processing the data that it stores. So this is a shared noting approach. Here we present another approach. We will briefly outline another approach, which is basically a shared memory approach using massively parallel processing architecture, in this case GPUs. So the approach is very similar to what we introduced with the Hadoop reasoning for RDF. Again, the rules which are comprised only of one triple on the left-hand side, one antecedent, they're trivial. The challenging rules are the joins. So again, the authors employ this rule reordering approach, which minimizes the subsequent reactivation of some rules, and it leads to some phases which can be finished in order. So yeah, the shared memory architecture, the GPUs provide really huge processing power at a relatively low cost. So on a GPU device, you can have like really tens, hundreds, or maybe you can go up to thousands if you combine several devices computing cores that are able to process input data independently to execute the same the same code over the input data. So you have a possibility for really enormous data parallelism achieved. But at the same time, GPU architectures come with specific challenges and restrictions, and it's not actually trivial to just implement some algorithm, run it on the GPU, and for this algorithm to be efficient. In most cases, this implementation will straightforward implementation from a traditional CPU to a GPU is actually suboptimal and not efficient. It might even be much lower than the CPU, the original implementation. And the major challenges are related to the specific way that memory is managed in such GPU systems. Basically, the amount of local memory that each thread, each processing element has very quick access to is very small, very limited. Accessing other parts of memory is very expensive operation. Synchronization is also very complex and very expensive between the various processing units. And also, if your algorithm, if the control flow logic basically has a lot of branches, this will additionally reduce the efficiency of the GPU implementation. It is most efficient when basically all the units can really execute the same instruction set, and there are no branches in the control logic that will lead to suboptimal performance. So random memory access is very expensive, synchronization is very expensive, control flow is complex. So very challenging. It is very challenging to develop efficient algorithms for GPUs. Anyways, quick summary of the results of the approach. So basically, similar to the MapReduce scenario where we have a mapper and reducer for each rule, basically the authors also implement one rule, one OpenCL kernel or thread to handle a new triple from the input. Basically, these kernels are responsible for making the joins to the schema triples, which are stored in a different way. As we said, this is a massively parallel architecture, so there are hundreds or maybe even thousands of such kernels, such threads executing in parallel, each of them consuming one input triple and making all the, if possible, making an inference, making a join to a schema triple and making an inference and producing a new triple. Excuse me. Again, the challenge is duplicate removal. And if you remember this 1:50 ratio between the unique and the duplicate triples that was reported in the Hadoop case, actually the authors here report a much higher duplicate ratio. So duplicate removal is very challenging. And in the case of a GPU, it's also very expensive because, as I said, memory management is very complex. First, memory access is very expensive. Memory transfers are very expensive, but basically managing structures in memory and allocating, relocating new memory that you may need is actually expensive. And even doing lookups to verify that some triple is, if some triple is duplicate or unique, it's a very expensive operation. So the summary of the benchmarks that the authors published. The computation on the GPUs is actually 5 times faster than the reasoning. So the reasoning implementation on the GPUs is 5 times faster than the equivalent implementation for the CPU. But if you take in mind the overhead of the communication, the memory access to the host of the system where the GPU is deployed to the main memory, and all these memory management complications, actually all these 5 times speed up it is lost basically because of the overhead induced by memory access, memory transfer. And these are the final times, including the everything related to memory management and memory transfer. So the summary is, this is again a promising area of research, but more complex strategies for optimizing the duplicate removal and minimizing these costly memory access are required in order to really achieve something similar to this 5x speed up. And the last part is really about mentioning benchmarks. Basically, we talked a lot about big data, and BSBM is one of the oldest Sparkle and RDF benchmarks. What is important is that in this latest version from April 2013, the BSBM benchmark includes a standard test of up to 150 billion triples, which is 750 times more than the previous BSBM benchmarks. So basically, this confirms the trend that people are really interested in more real-world scenarios, realistic data volumes, and not really on very simple, very small proof-of-concept scenarios. And of course, the benchmarks reflect this, and they will provide a more realistic evaluation of the performance of various RDF databases. And yeah, final remark, LDBC, another the Linked Data Benchmark Council, an industry-neutral non-profit organization. So benchmarks for RDF graphs and triple stores similar to the TPC from the relational database world. And again, big data volumes and complex queries to reflect realistic scenarios will be considered. And summary, because we run out of time already. So summary of all these points that we briefly discussed in the last couple of hours. Linked data is a good fit for the variety challenge of big data. Linked data can simplify. Linked data can contribute to big data by simplifying data discovery, data access, data integration. Basically, by enriching data with metadata, we can simplify these processing tasks. There is an exponential growth of linked data in the recent years, not only on the linked open data cloud, but also in various enterprise scenarios. The benchmarks that we talked about just a minute ago, they start targeting bigger and more realistic real-world data workloads. Very interesting research related to scaling up linked data for the volume and velocity aspect of big data. So we outlined already the NoSQL data stores for RDF data management and querying, Hadoop, the distributed processing system for RDF reasoning, and also GPUs, shared memory, massively parallel systems for scalable RDF reasoning. And yeah, basically we outlined the various research initiatives for adapting linked data and Sparkle for streaming data scenarios. And this is the end. Basically, the content of the Euclid webinars and the ebooks is available via various channels, and you can follow the progress and updates from the project, again, via Twitter or SlideShare, various other channels. Thank you.